You are listening to The Vocal Technologist. Spoken tech for your ears.
All right, welcome back. The material you brought together for us this week, it tells a very specific story, doesn't it? It feels like the honeymoon is over. We are way past the easy adoption phase of cloud and containers. Now we're hitting a massive efficiency crunch.
That's it, exactly. That's the critical takeaway. Our goal today is to give you the essential knowledge, the actionable nuggets you need for the 2026 DevOps landscape. We're not just talking about if you use Kubernetes, we're talking about really optimizing it, staring down this astronomical cost of cloud waste, and recognizing the huge cultural shifts that are hitting us.
So we're basically going on a targeted raid to figure out how to stop bleeding money and start demanding better quality from our systems and, frankly, from ourselves. We'll be hitting everything from PostgreSQL updates to why some people are loudly proclaiming that software craftsmanship is dead.
And if you zoom out, the theme is just. It's undeniable. We're moving from basic functionality into an era that is intensely focused on efficiency, on cost attribution, and high-fidelity automation. And here's the irony, right? The better the automation gets, the better our human input and our design thinking needs to be. Much better than we've shown in the past.
Okay, let's unpack this. Starting the top, strategy. The whole spending environment has changed. So what are the big non-negotiables we're seeing in 2026 for hybrid cloud?
The focus is overwhelmingly on regaining control. It's consolidation after years of just sprawl. The information points to 5 big shifts. First, AI-driven automation. Second, a much heavier, more disciplined reliance on policy as code for everything. Third is dynamic secrets management. Fourth, continuous cost management baked right into the pipeline. And finally, unified lifecycle platforms.
That sounds great on paper, a beautiful blueprint for control. But isn't there a hidden cost? The complexity of actually doing all 5 of those things at once? I mean, that could create its own drag, right? Unless the tooling is absolutely flawless.
That's a fair challenge. The complexity is only absorbed if the implementation is really well automated. But the need for these strategies is driven by that shocking waste problem.
Yeah.
Which brings us right to the painful numbers in that cast AI analysis.
Right. Tell us what they found when they looked at real-world Kubernetes usage. Because the numbers I saw were truly jaw-dropping.
They analyzed 4,000 live Kubernetes clusters. It's a massive sample. And they found severe over-provisioning just everywhere. The average CPU utilization was hovering near 13%. And memory wasn't much better, barely hitting 20%.
13%. That's practically criminal. So for every $100,000 you're spending on compute, you're effectively just lighting $87,000 on fire. Why is it consistently this bad, even with all the auto-scaling tools we have?
Because the complexity of container workloads just defeats generic auto-scaling. It's really hard to predict the peak demand for hundreds of interdependent microservices. So engineers, they lean towards over-provisioning to avoid getting paged at 3 a.m. And the management structures don't really incentivize shaving off that last bit of waste.
So we need specialized tools. The traditional FinOps dashboards, the pie charts, they're just not cutting it.
Precisely. Platform engineers need modern tools that integrate directly into their workflows, not some separate dashboard management looks at once a month. The requirements are tough. They need Kubernetes native visibility to see inside the pods. They need an API-first architecture for automation, and they have to be GitOps compatible. That's the only way to tackle the really complex task of attributing costs down to an individual microservice. You have to know exactly which line of code is responsible for that 13% average.
Okay, that resource waste is a painful reality check. But let's look at how Kubernetes itself is providing some relief, specifically with the v1.35 upgrades. Some of these features offer immediate, substantial ROI.
Yeah, and what's fascinating is how simple functional changes can unlock these huge financial benefits. Take the new alpha feature, restart all containers. Historically, if a pod needed a reset, you had to delete the whole thing and recreate it.
Which is heavy. It's slow, it's disruptive, especially with large images or stateful components.
Exactly. This new capability enables an efficient in-place restart of all the containers inside a pod without deleting the resource itself. Now think about a huge environment like a 1,000-node cluster running AI or ML workloads. The recovery overhead there is massive. This feature lets you do a fast reset from the last checkpoint instead of a full recreation.
And what's the tangible impact there? This sounds like more than just a minor convenience.
Oh, it's a huge financial boost. For clusters at that scale, the estimates we're seeing suggest this could save an organization over $100,000 a month. Just by cutting down recovery time and resource waste during that restart cycle, it's surgical efficiency.
That's phenomenal ROI. Okay, v1.35 also brought in better scheduling logic. Tell us about the extended toleration operators.
This is a really nuanced control point that's going to appeal to anyone managing strict SLAs. This alpha feature adds greater than and less than operators G and LT to the spec.tolerations field. Before, you could only do an exact match.
So if I'm getting this right, we move from just asking, does this node have a high cost taint, to being able to say, only run this workload if the node's utilization is less than 50%.
Precisely. It unlocks threshold-based scheduling. You can distribute workloads based on dynamic performance-aware criteria. It's a huge step beyond simple taint-intolerant logic.
And while we're optimizing, we have to talk security. Let's pause on that CSI update. If this new beta solution is just changing where the token goes, what was the actual vulnerability they're closing off?
That's the critical question. So before, CSI drivers might get sensitive tokens through the generic volume context field. The problem wasn't the token, but that Kubernetes components often log the entire contents of volume context during routine operations.
Ah, so the logging infrastructure itself became the vulnerability. You've got credentials being written to log files just because they were in a generic data bag that was designed for debugging.
Exactly. This new beta feature routes the tokens securely through a dedicated secrets field instead. It closes that specific vulnerability, the one mentioned in CDE 2023-2878, by making sure sensitive data is handled in a way that bypasses that generic logging. It's a classic case of being explicit about data intent.
Powerful lesson. Okay, let's pivot entirely. Because no amount of tech optimization can save us if the cultural foundations are, well, crumbling. We have to tackle this provocative statement that software craftsmanship is dead.
It's a harsh diagnosis, but the evidence is
Yeah.
compelling. Why would anyone say this? Because modern development incentives just overwhelmingly prioritize rapid feature delivery and short-term metrics over almost everything else.
So you're saying the very structure of agile and quarterly reviews actually incentivizes speed over durability.
Absolutely. The pressure to close the backlog, combined with the low perceived risk because CI/CD can fix things quickly, it has led to a collective de-emphasis on long-term code quality. It's a death by 1,000 paper cuts to the integrity of the code base, and it's all driven by business pressure.
So if quality is suffering, we have to counteract that with fundamentally better design, especially for failures. Which brings us to error design. We can't just keep forwarding opaque exceptions up the stack.
That's right. Most error handling today fails because it treats the error as a symptom, not a designed artifact. It doesn't preserve actionable context, so neither a machine nor a human can figure out how to recover. An unhandled error should mean the system can't handle it, not that it doesn't know how.
So what does a well-designed error look like?
It requires intention. Errors should be flat, with action-oriented kinds and statuses for programmatic recovery. Think HTTP status codes, but for internal state. And crucially, they must enforce context capture at system boundaries. When a failure crosses from the payment service to the fulfillment service, the error object has to explain exactly what happened, where, and what the next step is. It turns the error into a piece of API documentation.
That's a huge mindset shift. It turns errors into a recovery pathway. Speaking of recovery, let's talk about the paradox of automation, especially with AI agents. This takes us back to that 1983 paper from Lizanne Bainbridge. How does that old wisdom apply to supervising modern AI coding agents?
The core paradox absolutely holds true. In fact, it intensifies. The irony is that successful automation making things easier 99% of the time demands a greater investment in human operator training and interface design.
Because the human supervisor is now left to handle only the rare, catastrophic exceptions, and usually under a lot of pressure.
Exactly. When the AI fails, it can fail spectacularly. The human needs two things: a superior UI with crystalline clarity on what the AI is doing and continuous training. The chances to intervene are so rare that the skill could just atrophy. You have to train for the exception.
So when we use tools like GitHub Copilot, we also need a structured method to make sure we're getting both speed and accuracy, which brings us to the WRAP method.
Right, WRAP is a great little framework for this. It stands for write clear issues for the AI, refine the instructions until they're unambiguous, break work into atomic tasks, and then pair human judgment with the AI. It recognizes the human is still the director and the quality control, even if the AI is doing the typing.
Okay, let's widen our view again. Two massive pieces of core infrastructure got important updates: data pipelines and databases. What's new in Apache Spark 4.1?
Spark 4.1 introduced a couple of huge features. First, Spark Declarative Pipelines, or SDP. It's pushing for a more declarative approach to data engineering. Second, and maybe most exciting for some applications, is the new real-time mode in structured streaming. Real-time mode. What benefit does that unlock?
It's a phenomenal latency game changer. By optimizing the engine for stateless workloads, it achieves single-digit millisecond latencies. So for things like high-frequency fraud detection or IoT command and control, this moves Spark into territory that used to be reserved for highly specialized engines.
A huge speed boost. Meanwhile, PostgreSQL, the rock-solid backbone for so much of the internet, gave us a major quality of life improvement in version 18.
Yes, the enhancements to the returning clause are, surprisingly, one of the biggest usability wins this year. PostgreSQL 18 introduced the old and new aliases across insert, update, delete, and even the merge statement.
And why does seeing the old and new W values atomically make a developer's life so much easier?
Because you can access the row state before and after the change in a single atomic operation. It dramatically simplifies auditing and change tracking. You no longer need complex database triggers or extra select queries just to figure out what changed in an update. It's all in one clean statement.
That eliminates so much glue code. Okay, finally, let's wrap with a lesson in resilience from the Unkey migration. Wait, isn't this counterintuitive? Serverless is supposed to reduce complexity. Why did shifting back to stateful Go servers improve things for them?
It's a brilliant example of choosing the right tool for the job. They deliberately moved from Cloudflare workers to self-hosted stateful Go servers. The result, 6 times lower latency.
6 times, just from changing the platform. What was the culprit?
Network latency from external cache lookups. In the Cloudflare architecture, every API call had to go over the network to a distributed cache. By moving to stateful Go servers, they eliminated all those network hops and simplified their pipeline to straightforward in-memory batching. It reduced their complexity, it gave them platform independence, and it just made the whole system easier to reason about. Sometimes reducing network hops is the ultimate win.
We've covered a massive amount of ground. From the $100,000 efficiency gains in Kubernetes to the crisis of software craftsmanship and the power of atomic database operations.
The takeaway for you listening to this is pretty clear. The era of velocity driven purely by shipping features is just not sustainable. In 2046, efficiency is the new driver of velocity. Resource efficiency, developer efficiency, architectural efficiency. You have to cut waste to sustainably increase speed.
So what does this all mean for the bigger picture? Where do we go from here?
Well, consider this. Riot Games, a massive billion-dollar platform, recently locked millions of players out of League of Legends for hours. Why? Because they forgot to renew an SSL certificate, a basic administrative mistake they'd actually made 10 years before. We get so focused on AI and advanced automation, but if a company that big can fail because of a neglected renewal, how much more critical is it to invest in the boring, systematic removal of unnecessary manual work? It just echoes that famous Google engineering lesson. Long-term impact comes less from clever code and much more from systematically removing complexity.
A timely and maybe sobering reminder that the most advanced tech requires the absolute best fundamentals. Thank you for walking through all of this with us. We hope you got plenty of actionable insights for your next sprint. We'll catch you next time.
Spoken Tech for your ears.